I'm Drago. I lead research at Waymo. Today, I will tell you about some of our work. Waymo is Waymo's Alphabet's autonomous driving technology company, and the ability to handle a wide range of situations safely is key to our domain. So I will tell you some of our recent research towards that goal. So let me start with a bit of background on Waymo's history, which can be roughly divided into two stages. The first stage in the space like autonomous driving, which started in 2009, is to determine, is it possible? Can it be done safely? And the problem, you guys probably know by now, ended up being far harder than the industry thought when the program was started. It was relatively easy to show a compelling demo, but safely handling the broad range of situations and conditions that one encounters on the road proved quite challenging. We went driverless first in 2015, but it took several more years to lay the groundwork for a public AV service. And our Waymo One service opened to the public in 2020 in Phoenix East Valley. And since then, we have been at the stage of scaling out our usable product and service. This scaling out continues today and is accelerating. Today, we operate our service 24/7 in an area that's larger than 250 square miles in San Francisco and Phoenix, these two cities. And every week we serve tens of thousands of paid public rides a week to customers in these cities. We have been quite enthusiastically received by a lot of customers, and we look forward to keep improving this and bring it to more cities. The next two cities we have announced that we will be in is LA and Austin, Texas. For LA, we have already started doing driverless demo rides, so Los Angelenos can experience them in areas like Santa Monica and others. And as we drive, I want to show you some of the situations our vehicles have encountered and handled in driverless mode in the last few months. So here are first a bit more common situations, I would say. So this is us driving a tunnel and pedestrian is walking down here. Not common. You shouldn't walk on roads in tunnels. This is us handling heavy rain, and we also drive in heavy fog as well in San Francisco. But you can see here, there's interesting artifacts on the lighter points and so on. Here is us driving on the metal bridge. Okay, the metal bridge maybe not that interesting, even though for radar and so on can have interesting artifacts. Here we get to a construction scene. We need to understand what the construction worker is telling us. This is another example of a construction scene. So here it's somewhat interesting. So they hold a stop sign, but tell us to go. So we start going and then we say, oh, well, maybe it's a stop. Okay, well, you tell us to go. So we keep going, right? But you can see here the semantic understanding of the scene, colored ladder points. Here we are driving a narrow street, which are quite common. And there's an open door with a person there. And we need to negotiate with pedestrians that insist walking on the road in this scene as well. That's an example of things that we need to handle. One more scene here first. Maybe what's interesting is vehicles emerge because of the incline fairly closely. And then the more interesting part is here we see this vehicle deciding to back up. So we need to actually leave them space and understand what they're doing. This potentially even blocks a little bit of the traffic here, but that's the safe thing to do. This vehicle now parks and we continue safely, right? So I want to show you, these are some examples. Now, let's move on to more out of domain examples or heavier so. So this year for the first time we did, I'm going to speed this up a little bit. Let's see. 2x. So this is Halloween. So we had actually a service operating on Halloween. This is a big crowd of people and animal dressed people and construction worker and furry, I don't know, sign carrying people. And you can see, by the way, our perception sees quite far, even in the dark with these crowds. Here's our vehicle. Here's all the people we traced. There was Waldo. And then eventually we decide, okay, so we'll get out of this scene. So we make a 3-point turn because these people are not going to open up the street. I guess it's a festive location. So then we need to navigate between the crowds that, of the party goers. That's an example just from this Halloween Fresh. Some other things, you may have seen them before from our experience, barbecue grill falling from a truck and moving around on the highway. Can you guys hear me? Anyone say something? Okay, great. Sounds like you can say stuff if you want to. Here is, well, a traffic sign moving across the road with the worker carrying it. So you need to make sense of what this means. Or here is a house on wheels, right? And so on, right? And so we have to handle a lot of these cases. I will present some of our recent work, research on 3 topics: perception, prediction, and planning, and starting with perception, specifically open set perception. Let me define the concept. So many object detection benchmarks provide training data for a fixed set of object classes, and then they test the algorithm ability to detect these classes, right? And maybe a subfield focuses on particularly rare examples of these classes. We actually have interesting work in ECCV last year, which proposes an effective way to identify and leverage rare examples automatically in data. So if you're interested in this topic, I suggest you check it out. But this year, I'll talk about open set detection. These are objects for which we don't necessarily have any ground truth. We may not have seen them at all. And if you think what this could look like, so here on the bottom, maybe long tail, unusually long bikes, or interesting motorcycles with baskets. Here, okay, so maybe there can be airplanes on the road and dinosaurs, but you wouldn't necessarily expect it or necessarily ever see it in your training data a priori. So we need to be able to handle these two, right? It's not okay to collide with them, even if they appeared, so we need to think about it. And I will introduce first the work of ours from last year to set up the space. I think this work focuses on automatically discovering and auto-labeling 3D objects in the scene and their motion in a fully unsupervised manner. Generally, this paper is an instance of, I think, early work in an important domain. By design, our vehicles have a rich set of sensors that see the scene in images in LiDAR and more in real time over long periods of time. I think it should be possible to learn to parse this scene and track all the objects in an almost fully automatic way. I think that's a very promising direction for perception tasks. So for those of you working on perception, computer vision, there's a lot of interesting modern tech that can be applied, and I think a lot of headroom. So I generally encourage you to work on this. So before we get into the method details, I want to explain why we're interested in auto-labeling 3D bounding boxes. So in our domain, we believe that it's important to have some kind of intermediate representation and structure in the scenes that helps us understand if our plans result in safe driving outcomes. And 3D bounding boxes are a minimal representation that helps us understand the shape and motion of moving objects on the road. And so, yes, you could have other representations, but ultimately, for most agents and obstacles on the road, 3D bounding box is a very convenient sparse representation. So we focus on this one in this work. And what is the core idea? Well, it is to look for moving objects, segment them, and then try to align the segments and construct the final bounding boxes for the object. So it's unsupervised motion-based. And this is powered by these 2 boxes here. These are 2 modules in our paper. One is scene flow estimation. This is done in an unsupervised way. We first identify and remove ground and static points with some simple heuristics. For the remaining connected components of potentially moving objects, we apply, at the time, a state-of-the-art neural scene flow prior model, which doesn't need ground truth to generate reasonable estimates of point-to-point flow. And you armed with this flow, then we revisit these segments and we cluster object proposals. We track them using Kalman filter. We do some accurate registration to reconstruct a more complete shape of the object. And that allows us to then annotate the model box. A model box is the our estimate of the full extent of the objects, not just the visible part as you start here in tracking. Right, so you get this ground truth tracked bounding boxes for objects with this pipeline fully automatically. And then what can you do with it? Well, you can train detectors, and you can train, camera 3D detectors, camera lidar 3D detectors. Here we train the simplest, very standard point pillars neural network to detect any moving objects and estimate their flow or motion. This is the different colors indicate the various directions that the object's traveling in. And brightness is the magnitude, you can see. So you can see that a lot of vehicles, motorcyclists, potentially pedestrians also on the side are, we learn to detect them without any human involvement. Now it's not perfect, there is noise, but it also can detect a lot of very interesting, challenging scenarios, like some of the ones I showed before. So people carrying plywood or trash cans and other things. And generally, with this method, you can show that we can do well, or at least improve a lot on previously unseen classes. So if you hear the baseline is some supervised method that we give it bounding boxes for vehicles, but then it doesn't detect pedestrians. So if you give it VRU is vulnerable road user, that's pedestrians and bicyclists. If you give those, then it doesn't detect vehicles. If we augment the ground truth labels with our automated labels, then we learn to detect them in some decent way, a lot better than before. And also we learn, I'm not going to go in details here, but if you use the object tracks, you can also train behavior prediction models. And here, lower is better. Essentially, you guess closer to where the object is going to be. Our automated labels help, right? So it's a first step. I think it's interesting. I think the problem is more interesting even than the solution here. And the solution has some shortcomings, right? Or limitations. One is it doesn't deal with static objects. Second, it does not assign semantics, which often is quite helpful to objects, right? And so now let's try to rectify these issues. And of course, what can we rectify them with? Foundation models or vision language models are prime candidates. So this is recent work building on the past approach. So this was the first approach, transferring the knowledge of a 2D vision language foundational model to this 3D detection task in autonomous driving. And so, you guys don't need primer on the benefits of vision language foundation models. They have all this internet knowledge gleaned from the web. They're trying to capture it. We want that knowledge to be applied to our domain. Now, how do we do that? We have the images, right? And we want to train 3D open vocabulary models. Well, the key idea is our sensors are calibrated between lidar and camera. We can use the lidar camera associations to transfer these embeddings from the large vision models to the 3D scene, right? And there's past work doing this, but we're going to apply this to object detection and tracking. So how does it work? We have two stages. One is we do unsupervised multimodal auto-labeling. So you maybe start a bit like before. You have the point cloud sequences. You can create some boxes and tracklets, but now you have one additional input, which is the embeddings from this big vision model for every pixel. So what these embeddings allow us now is we can project them to the lidar points in the scene, so we can ground them in 3D. And the other part is that these embeddings are meaningful and helpful to create even better boxes and tracklets than what just unsupervised flow can do. So now we create this ground truth, leveraging the vision model. And one thing that we do is, since bounding boxes primarily make sense for objects you want to agents in the road and things that may move or you may want to track, they make less sense for stuff like road building, fence. And so these, we can explicitly ask the model to mark for exclusion. So we drop all of those, and we can use the semantic knowledge to facilitate it. So you get essentially better ground truth here. And then you distill it into a detector like before. Essentially, now we can train a open vocabulary 3D object detector to distill the pointwise feature and also to detect boxes and track them. And this new detector now can be queried with new objects of interest. So if you want to say, hey, where are all the trucks, we can now do essentially cosine similarity to the pointwise features produced by the model. And since this model is aligned to produce compatible embeddings. Now you can also get classes, novel classes, even for things you have not necessarily seen by virtue of doing this. And here is the comparison to before. So on the right, we have the first work I showed, which is purely based on motion, and it fails to detect the parked cars and has more false positives. Here is the new work that leverages vision language models. And of course, you also get semantics and can track pedestrians that move very slowly. Previous work had limitations. We resolve it, a little bit of video showing you that we parse a large amount of the moving agents of the scene without any labels. Again, I think in industry, traditionally, right, a lot of these problems were solved with human labels in the loop. And here we pushed the envelope some towards fully automatic solutions. But I think that's generally more to do. Moving on to behavior prediction. We also recently successfully applied ideas from large language modeling to this task. First, I will give you an example or primer on a modern behavior prediction model following, say, a recent paper of ours, Wayformer from ICRA this year. So what does this models typically do? So you have some kind of scene encoder implemented as a transformer model that combines or encodes the information present in the various elements of the scene, which can be our past history of the self-driving car or autonomous vehicle, traffic light states, road graph, and the behavior of other agents. And now for every agent, we predict k possible trajectories, which are things that the agent could do, right? With this kind of Gaussian mixture model style decoder. So you can have these 8, maybe you have several k trajectories, each is maybe 8 seconds long. And I call these marginal a posteriori predictions. These are independent predictions. Given the scene, what are the top k things each agent is likely to do, right? Now, that's a very convenient and simple thing to do, but these type of predictions don't capture the possible interactions between the agents. So here, in this picture, I show you 2 agents, the blue, and we have 2 of their most likely predictions, right? And these 2 very likely predictions happen to collide. Why? Because they were done independently of each other. So these agents actually interacting. They observe each other. Typically, such an occurrence will be very rare. One of them or both will react in some way. This model does not capture that. That's problematic, right? Now, why do people like these marginal posteriori models? Well, one reason is that it's difficult to do joint predictions. The space is exponential in number of agents, and the number of agents, worst case, can be hundreds, if you remember my Halloween scene. So there is a diverse set of work trying to address this, but honestly, obtaining strong performance on this task is still a challenge. And let me now introduce our work Motion LM. This is from ICCV this year, very recently. It treats the agents as participants in this constant conversation or dialogue where agents exchange actions and reactions between each other, a bit like communication. And so just as today's language models can capture sophisticated distributions over conversations, can we leverage similar sequence models to forecast the behavior of road agents? So following the parallel with language, in this work, we discretize the set of possible agent motions into these motion tokens. So there's one motion token for every time step, discrete. And the combination sequence of them comprises interactive future. So to train this model, we introduce a causal cross-attention decoder, and we train it using teacher forcing, where previous ground truth is not predicted, but just fed in, and then we predict the next step, discrete step, or really the motion of each agent over time. And future, well, tokens are predicted by attaining all the past tokens and potentially the scene encoding. And at inference time, we iteratively sample the outputs in the same causal way. So we just generate them sequentially, and then you get, depending how you sample, out of this prediction head, you can generate different futures by sampling different tokens and continue the simulation. So very similar, I think, to language models. And here is an example where, similar to before, you have marginal predictions colliding because they don't model the interaction. Here's our model capturing an intuitive interaction where the pedestrian goes and the vehicles gives them right of way and follows. This model has a couple of very appealing properties where we can trade off compute for quality. So one thing is, here's maybe a bunch of tokens of motion that this agent can do. So we can keep sampling. So the more we sample, the better our performance gets on the metric. So blue is better higher, red is better lower. As we generate more and more and more samples, it's more and more expensive, but we can obtain higher and higher quality on these metrics. So that's adaptive property. It allows us to trade off available compute for quality. And there is also another way to trade off compute for quality. We have freedom of how we discretize these tokens. So if we have one token, essentially this is 1/8 hertz, so 8 seconds, one token, that's a single marginal prediction. It's a special case, right? The initial state. Then you have fairly poor quality. And as you increase the frequency of agents observing each other's behavior up to 2 hertz here, so everyone reacts to each other every half a second, you can see the quality significantly improving here. Lower is better in these metrics. Right? And this method achieves maybe one of the first methods I've seen that does this iterative rollout and is actually competitive with what we call single shot models that try to predict single futures, a lot of these. And how do we tie it to this talk? So this is an out of distribution detection. So it's better on these two metrics, miss rate and mean average precision of whether you can predict trajectories where the ground truth was given the scores and the limited budget. Essentially, these two last metrics are a measure of how often you predict rare trajectories. They're a lot more sensitive to this, and this model is better at it. So this type of modeling, I think, is helpful in predicting rare behaviors compared to alternatives that try to approximate or simplify the output space. Last, let me talk a bit about planning. And here, I'll talk about a topic that's, I think, very important, and people tend to sometimes underestimate it, which is the importance of data sampling or intelligent data sampling for training high-performance planners. So consider the standard machine learning planning setting. You want to do reinforcement learning or imitation learning. And for the purpose of this section, I'll focus on the imitation learning approach, where we're learning a policy directly from expert demonstrations. And typically, you have some data set of expert demonstrations, and you just train on it, and all the data samples are treated equally. However, this can produce policies that are not that robust in challenging safety-critical scenarios. We can, of course, keep increasing this data set, but it's not clear that's the best thing to do. And so we had this past work at Iros, where we had an imitative route condition planning agent, continuous action policy trained with model-based Gale and behavior cloning. And we had certain performance of this agent trained on the whole data set. And then we randomly subsampled 10% of the data, and we expected the performance to get much worse. So this is failure rate, like if you have collision or fail to follow route or go off-road. So we expect, oh, with 10% data, we should be much worse. In fact, we potentially, in some cases, could even get better. So that's not very intuitive. You want that just simply naively increasing the training set does not strongly improve performance. That's not great, right? So, and that's because the vast majority of driving situations are easy. So in about 3/4 of our data, there are, well, no moving agents other than us in this case. And in some cases, they're moving, but they're far away, so nothing interesting happens. And here we're interacting, but it's still not too challenging. And the small sliver is the challenging scenarios. And we have a paper where we show how to upsample the challenging and interactive scenarios, showing how much of a gain that can produce when we pick primarily examples that have the most useful information. Of course, the big challenge here is, okay, well, what is your criterion for upsampling these scenarios? You want something that generalizes across different environments and policies. How do you do it? And in this work, we propose a learned difficulty model, which works like this. So, right, at a company like Waymo, we have a fleet. It can collect experiences with multiple different platforms and potentially in different regions, and potentially with, right? And then we collect them. So these are, we chunk it into what we call run segments, the snippets of recorded driving data that we may want to replay and test our performance in. So then we run development planners, different kinds, on this data and observe whether we have encountered interesting situations or potentially collisions that need work or addressing. And there's optionally even humans that validate that the simulations you've done are realistic and potentially there are cause for concern or things to improve. And so we create this data set, right? And this data set of simulated collisions and near misses are sent to human triage. And so then we take them and we train a model of difficulty using this data set. And this model, because it combines rich data and result of many potentially different planners, should have a very strong zero-shot capability, meaning there's a good chance that even a different planning agent will benefit from the same difficulty signal. And so here is a distribution of the scores. You have, they're shown the different deciles in different colors. You have a lot of easy scenarios and then a long tail. And just some examples. This is a very easy scenario. Drive straight, yay. Here's a bit harder scenario. You drive next to some slow vehicles, and I think you need to understand traffic lights a bit too. And let me show you a difficult scenario. We're driving next to articulated bus really closely. We need to pay attention not to collide. Furthermore, down the line here, there'll be a vehicle that will push the bus to even swerve in our way. We need to be very smart what we're doing here. It's very easy to be in a collision, right? That's a difficult scene. And so using these difficulty buckets, we try several different sampling schemes to see what is most effective. So baseline is just you sample IID uniformly, which was what I showed before. You can just take the hardest examples and train using those. And there is, I think I'll just highlight this geometric variant, which starts with equal weights for every bucket, and over time upsamples the difficult scenarios. And then what do we see? So if you take this same amount of sample data from the original set, baseline is the worst, actually. All of the others perform better sampling strategies. And of those, geometrics is the strongest. Here is the effect of sampling. So this is a case where the baseline trained agent is unable to negotiate and maneuver in tight, narrow streets. And this is its counterpart, which was trained with the geometric schedule, handles the same situations, I would say with aplomb, right? Not so bad. Last but not least, geometric is appealing because if you just use the hardest examples, which is this blue, they improve on the hardest cases, but they make more mistakes in the easy cases, which they've never seen and out of distribution for them. And geometric, which is green, dominates baseline gray at every single decile. Do I have, how much time do I have? I think I'm almost done, right? I will just say another way to deal with out of distribution is reinforcement learning. We have some interesting paper this year in IROS on combining the benefits of mutation learning and reinforcement learning. We find these two quite complementary when possible. So we have, I think that's an interesting area to do more work. I think, and yes, reinforcement learning makes even better performance on the most difficult cases, even better. Maybe the last thing I will say is reinforcement learning is a very interesting topic, but to train these models, we need to have a simulator that's reliable enough for model training with as little human present in the loop. This is challenging because it requires high fidelity from the simulator. We want this virtuous cycle But for that, we need to build the right simulation environment and the right, I think, pipelines to be able to iterate. And I will just say we have recently provided a lightweight research simulator where you can experiment with training these types of agent models of the ones I just recently mentioned. And it's differentiable, hardware accelerated, written in JAX, multi-agent simulator on some of these simpler representations of road graphs and boxes. I think there is a lot of interesting topics of research similar to the work I just showed, and I encourage people interested to pursue it to check Waymax out. Thank you again for inviting me, and I hope I was able to tell you a little bit about the topics that are present in our domain. I think it's a very exciting domain, and I hope you guys engage more with the data sets and the challenges that we are working on. Thanks again, and thanks to everyone and Waymo that helped me with some of these slides.